Well, from the mathematical point of view, angular momentum is really indeed very convenient physical quantity to analyze things. However, if you think about your intuition, probably this is not the best. None of you would say that this is the most convenient or intuitive physical quantity to describe motion. What type of motion actually angular momentum describes? I mean, rotational. It is very convenient to describe rotational motion, right? However, I think you probably think about something else when you think about rotational motion. Another quantity, not angular momentum. What do you usually think? Yeah, we have better intuition about angular velocity. It is more visible. It would be also convenient actually to link description of motion with description of interaction using angular velocity rather than angular momentum. Well, so in order to do this, we already know how interaction is related to angular momentum, right? How? What law says that? Newton's second law. I forgot which version. I think fifth. All right. Well, we will now write Newton's second law for angular velocity. So if we just express angular momentum in that version of Newton's second law in terms of angular velocity, then we will have a relationship between motion and interaction in terms of torque and angular velocity. All right, so now I want to relate angular momentum and angular velocity. So let's start with the particle. If we look at the particle, well, in a rigid body, and it moves in a circular motion when that object rotates. So we concentrate actually only on the rotational motion at this point. Let's say that I'm now thinking about angular momentum about this point. Well, if object moves in a particle moves in along such a circle, well, so momentum is tangent. Well, this angular momentum is at an angle like that because it has to be perpendicular to both the position vector and the momentum vector. Do you see it? Can you imagine it? Yeah, think about it. Well, think that this is a particle, and let's say that it is traveling that way. Oh, actually, no, it circles like that. A big circle. And imagine that it circles in such a way that you are at the axis of symmetry of that circular path. What would, if the momentum is in this direction, figure out what is the angular momentum of this particle about you. Do it. Yeah, I mean, use your hands now to figure out what is angular momentum. Well, let's say from Mark. Yeah, so let's say position vector is up like that, right? Now, if particle moves there, so momentum is this way, right? So using right-hand rule, angular momentum would be at an angle like that. Do you see that? I mean, consistently with, if we look at this drawing, so it would be more appropriate to imagine that the particle moves in this direction. Yeah? So it circles Mark like that. So at this location, position vector is like is at an angle. Momentum is in this direction. So angular momentum is at an angle like that. Can you see it now? Do you understand the drawing on the screen? Okay, great. Yeah. So you see that angular momentum is not of a single particle. Is not in the same direction as angular velocity. Yeah, angular velocity, if an object moves like that, is straight up. Angular momentum is at an angle. In general, now, if we think about the total angular momentum of the object, we will have to add angular momenta of all the particles, and we will get some kind of a vector. And since for a single particle it is not aligned with angular velocity, angular momentum is not aligned with angular velocity, it means that in general angular momentum for an object doesn't have to be aligned with angular velocity. There is some well, and now let's mathematically, precisely relate all components of angular momentum with angular velocity. For simplicity of analysis, let's assume that that we align one of the axes. Let's make it z-axis to be aligned with angular velocity, and then we will find out what are the scalar components of angular momentum in this coordinate system. So z-axis is along angular velocity. Traditionally, actually, you will do it in many subjects. In chemistry, always any type of rotational motion is along z-axis. In physics, it's like that. I'm not sure about mechanics, but probably it's the same way. All right. So angular momentum of a single particle, its position of a particle multiplied by momentum of the particle. Total angular momentum requires that we add all angular momenta. All right, now velocity, if it is a rigid body, then velocity of ith particle, well, we always can represent it as a superposition of a translational motion and rotational motion. Well, let's choose a coordinate such a coordinate system that we have purely rotational motion. So in this coordinate system, velocity of ith particle is angular velocity of the particle. Now, for a rigid body, it happens that they all move with the same angular velocity. They don't move with the same velocities, but they move with the same angular velocities. All particles in a rigid body have always the same angular velocity. About that, I mean, I could actually choose a reference frame that they wouldn't, but I pick a reference frame in which they have the same angular velocity. And we have to multiply it by position of that ith particle. Well, now the next step is a mathematical step. Here I have well, I can take this mi in front and use a mathematical identity for a double vector product. And if I have vectors, vector A multiplied by vector B times vector C, I can write it down that this is scalar product AC multiplied by vector B minus AB, scalar product AB times C. I think I did it right. So look, that if I take out this mi, I have Ri times omega times Ri. Well, so if you look at this identity over here, first I take to multiply the first vector by the third vector using scalar product. I will get a number, and then I have to multiply this number by the vector in between. Yeah, vector B according to formula. So the vector B corresponds to omega. So I will have Ri times Ri using scalar product, which means that this is Ri squared times vector omega. And the second one requires that I multiply the first vector by the second vector using scalar product, multiplied by the third vector. Do you recognize that this is the same thing? I mean, we had this formula, but I mean, I know that we don't remember it for a long time. So when I introduced vector product, you saw that, but since then I never used it. All right. Now let's look at the individual components. Yeah, so here is how vector L is related to angular velocity, and we see that it is not in the same direction, right? I cannot pull out this angular velocity here easily and have a number and angular velocity. So let's look at each of components of angular momentum, and we will see that actually every component of angular momentum is affected by this one component of angular velocity. Which says that angular momentum and angular velocity are not in the same direction. All right, so let's now take a look at x component. Well, x component comes from x component of this vector and x component of that vector. All right, let's now see what is x component of this vector here, consistently with our choice of the reference frame. How much? 0, correct. We picked that angular velocity is along z-axis. So x component, so this term does not contribute anything to the x component of angular momentum. Now, from that one, we have to see what is x component of this vector here, right? So I have, and what is x component of vector Ri? By convention, I will write it just as xi. So here I will have xi. Now I have to multiply, find this scalar product. Now let's find out scalar product of this vector. Vector Ri has components xi. How about if I write it down? Vector Ri has components. How about if I write just scalar components? xi, yi, zi. Why don't I also write components of angular velocity? What are the components of angular velocity? Look at the picture. 0, 0, omega, right? Let's multiply those two vectors, yeah, because I mean this is what we have over here. We need to multiply these two vectors. What will happen if you multiply Ri and omega? How much is that? Right. Yes, so we have to multiply first component by first component. This gives me 0, plus this component times this component gives me 0, plus this times this. So it's just zi omega. All right, so we have this mi because it was there. From this term, we got 0. Now this, I copied this minus. I pulled out this minus in front. From the scalar product, I will have z times omega, zi times omega, and from this vector, I will have xi. Is it clear? All right. So this is x component. This is an expression for x component of angular momentum in terms when angular velocity is along the axis. So we see that in general it is not 0. Well, if I do the same thing now for y component, why actually you talk to each other? What will happen if I want to calculate y component of angular momentum from this expression? Talk to each other for a moment so that you really comprehend it. All right, so let's start with the contribution from the first term. How much this term is going to contribute to y component? 0. Very good, you are getting it. Right, now for this one, what do we have to consider well, let's start with the scalar product. What are we going to get from the scalar product? Zi omega, correct. And what are we going to get from vector Ri for the y component of angular momentum? Y, correct. Very good. Right? So the only difference that instead of xi, we have here yi. Now for the z component of angular momentum, we will have contributions now from both terms, from this and from that. All right, and here is entire derivation for it. Yeah, so here I have to, I mean, z component of angular velocity is this number omega. Now here I have to square vector Ri. Well, I have to take all three components, yeah, because now I have to, if we look back to here, now I have to square this vector. So it is xi squared plus yi squared plus zi squared. This is what I'm going to get for the square of this vector, and then I multiply by omega. Now that term comes really again from this expression, so it is identical like for x component and y component of angular momentum. Instead of xi over here, I need to put zi, and I need to take zi from this expression as well. All right, now the next step is actually rearrangement. I pull out that common omega and combine z. Z times z gives me z squared, so I have z squared. Now I want you actually to take a look what is Ri squared minus Zi squared. Just this expression. Ri squared minus Zi squared. We will have to take a look at over here. Well, Ri squared, I mean, if I consider this particle, it's the length of this position vector, right? So it's the distance from the reference point to the considered particle. This is what Ri squared is. It's square of that position. Now Zi is square of z component of this vector. Now let me draw it from a different point. I mean, from a different point of view. So let's say over here I have the reference point. Here I have the particle, and the particle, and they both are in the plane of the whiteboard. So this is ith particle, which means that, well, here I have a position vector Ri. Now let's make that this is axis z. X and y is toward us. So Zi is over here. And this is z component of this vector. Think now, what am I going to get if I take square root, not square root? Well, no, just difference. Ri square minus Zi square. It's not y component square. But you are on the right track. JD recognized that this is a right triangle, so the sides and the hypotenuse satisfy Pythagorean theorem, which means that square of this distance plus square of this distance should give us square of this distance, right? Well, which means that actually this difference, I will call it Ri prime over here, is equal to just Ri prime square. Now I made it Ri prime because I wanted really to align only, I mean, this particle could be here, for example, or there. So really this is the distance from the axis. Well, and this is what I did over here. So I wrote now that this difference over here, the difference of these two numbers gives me distance from the axis of the ith particle. So z component requires that we multiply angular z component of angular velocity by that, or magnitude of angular velocity by that number. All right, let's now think when does it happen actually, because there are situations that angular velocity and angular momentum are in the same direction. For what kind of objects angular velocity and angular momentum are in the same direction? Well, if they were in the same direction, what could we say about, what should be the components of angular momentum? We would have to know, if we can say something about two of those components, then we will know that they are in the same direction. What actually ruins the directional relationship over here, in the sense that they are not? Are they? If you look at these components, these expressions for components, is vector omega and vector L in the same direction? No. Why not? Let me just, how about if we play with something? Let's say that Lx is equal to 2 omega, Ly is equal to omega, and Lz is equal to 3 omega. Is vector L parallel? Is it parallel to vector omega? Yeah, recall that vector omega has scalar components 0, 0, omega. I could write actually vector L, therefore scalar components of vector L are 2 omega, 3 omega, omega, 3 omega. Is this vector parallel to that one? No. How about if I change it to omega, omega, 3 omega? Is this vector parallel to vector omega? No. What should I do to make it parallel? How about this vector? Omega 0, 0. No. Yeah, this vector is in z direction, this vector is in x direction. Maybe this one. Are they parallel? No. Give me a parallel vector. 0, let's try 0, 0, 2 omega. 0, 0, 2 omega. Are these parallel? Yes, these are parallel, right? Now, how did you recognize that they are parallel? Because what? Yeah, scalar product of each other. No, I wouldn't conclude anything from that. In principle, yes, we could calculate it, although there is a simpler way. They are going in the same direction. Yeah, how do you know that they are going? How do we know that they are heading in the same direction? What direction is this vector heading? What's the direction of this vector? Z, right? It is in the z direction. And this one? Z. How do you know that this one is in z direction? Because the other components are 0. Correct. All right, let's now go to the screen. So what should be Lx, Ly? What would you have to know about Lx, Ly, and Lz to recognize that vector L is in the same direction as vector omega, and omega is in z direction? That Lx and Ly are 0, right? These sums have to be 0. Well, omega doesn't make it yet, because omega is the z component of angular velocity, and it is a non-zero number, which means that this sum has to be 0 in order to Lx be 0. This sum has to be 0 in order to Ly to be 0. All right, I made that. All right, let's now think. What kind of, because when object has appropriate symmetry, these sums are 0. Try to find out what objects will have such symmetry. What do we have to have? How the particles, in other words, have to be distributed in order to have this expression to be 0. One is very, very easy. Look at z. Yeah, well, if we place particles all at the same height, and that height will be 0, then angular momentum is going to be, the z component and y component are going to be 0. Yes? So if I take sheet of paper, pick a reference frame in the plane of paper, angular momentum and angular velocity are going to be parallel in such a situation, because all particles are in the xy plane. So for them, all zi are 0. If I add a lot of zeros, I will get 0 value. All right. Now, how about actually if it is a thick object? So I see that if it is a sheet, I can have angular momentum and angular velocity in the same direction. Now, how about if I take it that way? That it's symmetrical also about the plane, xy plane. So every particle above the plane, I have corresponding particle below. Well, what will happen in the sum then? They will cancel out, because for certain particle mi at location zi, I will have a particle, identical particle. So for that particle, mi is going to be identical, xi is going to be identical. However, z is going to be opposite. So if I add, it will cancel out as well. So for an object which is symmetrical about xy plane, I also get that angular momentum is in the same direction as angular velocity. Well, one more. Okay, so actually this is the case. Now, also every time when the object is symmetrical about the axis of rotation. Because now for a particle on this side, I will have a particle on the other side. So for the particle on the other side, x's are going to be opposite and y's are going to be opposite. Z's are going to be identical. So if I have a particle with mass mi at height zi at location xi, I will have another particle at location for which xi is opposite. So it also cancels. Do you see it? All right, so for objects of appropriate symmetry, angular momentum and angular velocity are parallel. Now, most of pieces of machinery are made in such a way that angular velocity and angular momentum are overlap. Think about a gear or a pulley. Does a pulley, for example, for a pulley, does angular momentum and angular velocity overlap? Consult with each other why they overlap. I mean, why they are in the same direction for a pulley. And then think about a gear. Why for a gear we have it the same way? Now, when you go, I mentioned yesterday that when you go to garage to change your tire, they will balance your wheels. And they will do two things. Balance it statically to get what? To get center of mass on the axis of rotation. Because if you do that, then it will prevent the type of a shaking, right? Because if the center of mass is not on the axis of rotation, it means that center of mass will circle around it. And if it circles around it, well, we can see, analyzing translational motion of that wheel, yes, center of mass is accelerating all the time toward the center. So we need a variable force to do it. And that variable force makes the car to shake. The other type of balancing is dynamic balancing, and it is balanced when the wheel turns. And what they do is they now try to rearrange the particles in such a way that angular momentum overlaps with the direction of angular momentum overlaps with the direction of angular velocity. Because now think what will happen. I mean, the wheel, actually, when the wheel turns, the axis is along angular momentum or along angular velocity? Have a vote for angular momentum, that it is along angular momentum. You disagree with that? You are right. The axis, I mean, no matter if the wheel is balanced or not, it will turn how we force it to turn. So it is going to turn along angular velocity. However, if it happens that angular momentum does not overlap with angular velocity, the directions, well, it means that angular momentum is going to turn along a cone. All right? Now, what does it mean? If angular momentum is moving along a cone, it is not constant, which means that we have to apply something to make it to vary like that. What do we have to do? Apply the torque all the time. So now on the axle, instead of having this type of a shaking, we are having this type of a shaking. So when the angular momentum and angular velocity do not overlap, we have to apply torque on the wheel continuously, variable torque, and that variable torque now will make the car shaking too. So purpose of dynamic balancing the wheel is to align angular momentum with angular velocity, because then when they are aligned, when we drive the car, angular momentum of the wheel is constant. And if angular momentum of the wheel is constant, what can we say about the torque? The torque has to be zero. Correct. So the body of the axle doesn't have to apply a torque on the wheel in order for the wheel to roll. I'll try to prepare appropriate demonstration for tomorrow so that you can really feel what the body of a car experiences when the wheels are unbalanced. All right. And in the case when angular momentum is parallel to angular velocity, then the proportionality coefficient between them is this number. Now, this number is called moment of inertia of the body about the axis of rotation. And you have to memorize entire phrase, because if you say just moment of inertia, really these numbers, this number and this number also belongs to moment of inertia. You will study it more thoroughly in mechanics classes. For now, we will talk only about objects for which moment of inertia has only, well, is a scalar quantity, is a number, and angular momentum and angular velocity are parallel. In general, they are not parallel, and moment of inertia is a tensor quantity. We need 9 numbers, really, to fully describe rotational inertial property of an object. Now, what angular inertia is for rotational motion, we could compare it to another inertial property of an object for translation motion. So there is analogy. So moment of inertia describes inertia of an object. What other physical quantity we introduce which also describes inertial property of an object? Mass, correct. So what mass is for translational motion, moment of inertia is for rotational motion. Okay. Now we can think about next version of Newton's second law, which will relate angular velocity with torque. So, well, and we will do it exactly as I said. So, external torque is equal to the rate of change of angular momentum. Now, for an object of appropriate symmetry, so that version of Newton's second law is valid only for objects of appropriate symmetry, the symmetry for which angular momentum and angular velocity are in the same direction. I can write down now that angular momentum is equal to moment of inertia multiplied by angular velocity, and take moment of inertia in front of derivative, and then recognize that this expression is rate of change in angular velocity. We call it angular acceleration. So this version of Newton's second law says that for symmetrical rigid bodies, angular acceleration is proportional to the net external torque. Obviously, it has to be in an inertial reference frame. Well, we have just few minutes, so I'll show you actually this thing. Well, if I hold it like that, what will happen if I take away my left hand? If I do not support that axle with my left hand? It will fall over. Is this what you expected? That's good. Now I'm going to do the same thing with the wheel spinning. What will happen if I remove the support? It doesn't fall over anymore. Now let's try to figure out why does it happen. I mean, to see from Newton's second law, which way did I turn it? This way? Okay, just to make sure. Yes. All right. So if I was spinning in that way, what was the direction of angular velocity of this wheel? Show me the direction of angular velocity. What was angular velocity? Very good, that way. Angular velocity is perpendicular to the plane of the motion of the particles. It was spinning along this axis. Angular velocity was in this direction. All right, now let's figure out what was the torque. How about if we think about the center of mass? The torque about the center of mass. So who was exerting the torque? I was. What else? And the Earth. All right, let's estimate the torques. So about the center of mass. So what was the torque, gravitational torque? Recall that center of mass overlaps with center of gravity in the classroom. So what was the gravitational torque? 0, because position of center of gravity with respect to center of mass is a 0 vector. They overlap. So gravitational torque was 0. Now how about my torque? If I was holding it like that. I mean, obviously only with right hand here, because I released that hand. So force was up. I applied, let's say, force over here, right? So position vector was like this. Correct. So the torque was in this direction, right? So net external torque was in this direction, while angular velocity was in this direction. Well, which means, now if torque was in this direction, what was the direction of angular acceleration? The same. The same. The change in angular velocity was in this direction. Velocity, angular velocity, which had this value, was changing in that direction. Which means that, well, if we add a tiny change, alpha, angular acceleration multiplied by time, well, so it had to change from such a value to such a value, right? So angular velocity changed from this angular velocity to this angular velocity, and later on to this one and to this one and to this one, and it made this wheel to spin. Now, why did it fall like that if it didn't spin? Yeah, because now what was angular velocity now? 0. Okay, now when it is changing, it is also changing in that direction, right? So it starts to spin this way. Actually, we use this trick. I mean, I think that at least half of you have used this trick with a wheel. How? Ride a bicycle. Now, not only ride a bicycle, but can you ride a bicycle without holding to a steering bar? Yeah. Now, how do you make a turn? Lean. What for? To apply a torque, right? Because, I mean, this is exactly what you were doing. Yeah. Now you lean to push on this side. You wanted now to apply a torque like that. And when you applied a torque like that, the wheel turned to the left. And you know that if you lean this way, the bicycle is going to turn left. If you want to turn right, you have to push on this axle and pull this axle up, right? So then the wheel turns to the right, and the bicycle turns to the right. Next time when you do this trick, think about 7th version of Newton's second law. See you tomorrow.